So our speaker is Aaron Thomas, and he will talk to us about RISC-V. Aaron, you have the floor.
Thanks. Going? Is the mic on? Yep. Okay, good. All right, so I'm Aaron Thomas, and I'll be talking about RISC-V, open hardware for your open source software. So how many of you have heard of RISC-V? That's a good number. How many of you were aware that RISC-V is actually pronounced RISC-V and not RISC-V? That's actually pretty good. Okay, all right. How many of you have played with RISC-V hardware or emulated hardware at all? That's a few people. And how many of you have read any of the RISC-V specifications? That's a good number. Okay, so there's some people who know things about RISC-V in the audience, so that's cool. So I'll give you a quick overview of my talk. I'll give you the goal is sort of to give you a tour of the RISC-V ISA, the instruction set, where it came from, kind of a quick overview and point you to the specifications. And then I'll talk about the ecosystem, so the hardware and software, the open source hardware and software that are available for RISC-V. And my kind of ulterior motive in coming here is to kind of grow the RISC-V community, so I'm hoping I can get you all interested in RISC-V and hopefully contributing to RISC-V and becoming a part of the community. So the talk, I'll start off with a little bit of a RISC-V 101, so a little bit of background on the ISA, where it came from, that kind of thing. Then I'll talk about the RISC-V hardware landscape. There's been a lot of kind of interesting developments in the RISC-V hardware landscape. We actually have RISC-V silicon that anyone can buy now, which is pretty exciting. And then there's a lot of open source SoCs and chips that are out there. And then there's been a lot of work in the software stack in the last 6 to 12 months. A lot of open source projects have been ported to RISC-V and things have been upstream. Thanks. So that's sort of the overview for the talk. Aha. Sure. I will do that now. Sorry. Is that better? Is that okay? Yeah, all right. Okay. So that's the overview of the talk. Give you a little background and then talk about the hardware and software ecosystem. So we'll start off with a little RISC-V 101. So RISC-V is an open instruction set specification. It's an ISA. So some of the other ISAs that you may be familiar with are x86, ARM, Power, Alpha, MIPS. So RISC-V, unlike them, is actually an open specification. So you can build open source or proprietary RISC-V implementations. It's completely up to you. It's an open standard, and you can do what you want with it. So if you tried to do this with one of the commercial ISAs, such as ARM or x86, you might get a friendly letter from one of their lawyers. Maybe not so friendly, but yeah. So the nice thing about RISC-V being an open ISA is that you don't have to pay any licensing fees. You don't have to deal with any lengthy contract negotiations, and you don't have to deal with lawyers, which I think is a good thing as an engineer. So, I mean, the licensing fees are a problem. So, I mean, if you're trying to build a really low-cost IoT device, the licensing fees can add up to a substantial cost for your specific device. Contract negotiations can be lengthy. It can take 6 to 12 months to come to a negotiation with ARM and other vendors. And that can kind of kill you if you're a startup and you've got VCs breathing down your neck. And yeah, no lawyers, so that's good. So I'll give you kind of a quick overview of RISC-V. So RISC-V has a very modest goal. And that goal is to become the standard ISA for all computing devices. So from microcontrollers to supercomputers, accelerators, basically any chip that you have in your iPhone system on chip, we want that to go from some sort of proprietary ISA. There's so many different proprietary ISAs to a single standard ISA, and that would be RISC-V. And so yeah, it's a modest goal. And so RISC-V is designed for research, education, and commercial use. And research and education were kind of the initial uses because this RISC-V actually came from the University of California, Berkeley. They were using it for research and education. And it's also becoming more widely used in commercial sector. People are building products on RISC-V. And if you go to the RISC-V workshops, it's kind of interesting. So I've been to all of the RISC-V workshops, and every workshop, there's like more people using RISC-V, there's more companies using RISC-V. There's a lot of interesting research that people are doing with like security extensions and memory models and silicon photonics. So there's a lot of interesting RISC-V stuff that's been happening because there's an open standard. So you can blame these folks for RISC-V. These are the responsible parties. So Krista Sanovich and David Patterson are professors at the University of California, Berkeley. David Patterson actually retired recently, so I guess he's a professor emeritus. And their students, Andrew Waterman and Yunsup Lee, are sort of the inventors of RISC-V. And so the story goes that Krista and the Berkeley architecture group, they were beginning to search for a common ISA for their research. So the way Berkeley works, or at least the Berkeley Architecture Research Group, is every 5 years they form a new lab to tackle some new problem. And so they were starting up this new lab, and they had used a bunch of different ISAs over the years. And they were like, maybe we should start reevaluating what ISA we want to use for this specific lab for the next 5 years or so. And so the dominant ISAs that are out there right now are x86 and ARM. And they have a number of problems if you're a researcher. So one is that they're fairly complex ISAs. There's a lot of instructions. If you've actually tried reading the Intel manuals or the ARM manuals, they're pretty long. There's a lot of stuff in there. If you ever see Krista Sanovich on the street, you should ask him about x86's AAA instruction and see what reaction you get. So the ISAs are just generally too complex for research, and so they decided against it. And then you have the IP issues. They're not open ISAs. If you try to tape out an ARM chip, you're going to get sued. So it's not really ideal for researchers. So then they embarked on, so as a result, they embarked on a 3-month project to develop their own clean slate ISA in summer 2010. And they continued to work on it over the years and kind of refining the ISA as they taped out more chips and gained more experience. And then 4 years later, 3 months turned into 4 years, they released the frozen RISC-V user specification in May 2014. And then as people became, in companies, academia, and various people became more interested in RISC-V, RISC-V sort of moved outside of Berkeley and became part of the RISC-V Foundation, and the foundation was formed in August 2015 to kind of caretake the ISA. On a personal note, I actually designed an ISA myself. I embarked on my own 3-month project. I co-designed an ISA for an undergraduate computer architecture course, and it was not a particularly great ISA. If RISC-V existed then, I would have used it. So yeah, I think RISC-V will be a good thing for researchers and university lecturers everywhere. So the RISC-V Foundation, which was recently founded, it's a nonprofit. Its mission is to standardize, protect, and promote the free and open RISC-V instruction set architecture, and also to help build up the hardware and software ecosystem for use in all computing devices. And so, as I said, the RISC-V Foundation is a nonprofit based in the US, and it has over 50 members, and there's a lot more members that have been joining or interested in joining, so we expect that to continue to grow. And there's been broad commercial and academic interest. So the last RISC-V workshop, the 5th workshop, sold out. We had over 350 people, and the attendance has been steadily going up. And so that pulled from 107 companies and 29 universities. So we have sort of a broad interest in RISC-V. So some members of the RISC-V Foundation, so you have some fairly large companies. So Berkeley, of course, is a member of RISC-V Foundation, but big companies such as Google, Hewlett-Packard Enterprise, Huawei, IBM, Mellanox, Micron, Microsemi, Microsoft, NVIDIA, NXP, Qualcomm, SiFive, Western Digital. You get the picture. There's a lot of big companies that are interested in RISC-V and kind of evaluating RISC-V for their products and research. Other RISC-V members, AMD, ETH Zurich, MIT, LowRISC. There's a lot of people who are interested in who are members of the RISC-V Foundation, and it's and actually these slides are out of date a little bit. There's been a few people who've been added, so it's the RISC-V Foundation is doing pretty well. So to go back to the RISC-V ISA, so RISC-V is the 5th RISC ISA from Berkeley. So the early RISC research was done at Berkeley and Stanford in like the 80s. And so they've done a number of RISC chips over the years. So this is the 5th RISC ISA from Berkeley, so it's RISC-V, so the Roman numeral 5 or V. And the nice thing about RISC-V is it's a modular ISA. So it's It has a simple base instruction set that's fairly small, and then you can layer extensions on top of it. So it has this base plus extension model. And so there are 32-bit, 64-bit, and 128-bit versions of the ISA. And yes, I did say 128-bit. It turns out data center people are interested in 128-bit. So the ISA itself the base ISA is fairly small. There are fewer than 50 hardware instructions in the base ISA, so this makes it feasible to implement microcontrollers in really small cores. And as I mentioned, it's designed for extension and customization. So you take a RISC-V core and you basically can customize it to your application. And this sort of comes from the base plus extension model. So to just kind of go over the base ISA, so there are different base integer ISAs for each word width. So the 32-bit RISC-V instruction set, the kind of naming scheme is RV32I, and I stands for integer. 64-bit is named RV64I, and 128-bit is RV128I. So the way RISC-V, the kind of naming scheme is that they have these one-letter names for extensions. So I stands for integer, and there are a number of other standard extensions. So M stands for integer multiply divide. A stands for atomic memory operations. F is the single precision floating point extension. And D is the double precision floating point extension. And so because all of these extensions are fairly widely used and necessary to boot up a general purpose operating system, they're lumped into this GISA. So this includes the integers, your multiply divide, atomics, single and double precision floating point. And this is the ISA that you'll use if you want to boot Linux or BSD or something like that. So in addition to the standard instruction sets, you can build your own non-standard extensions as well. RISC-V is designed for that. So kind of the cool thing about the RISC-V ISA is that it's small enough that you can actually fit it on a sheet of paper. So this is a green card for the RISC-V ISA. It's not actually green, but that's what they used to be called back in the day, or so David Patterson tells me. So the nice thing is that the base integer instruction set you can list all the instructions in one is basically in the left column. You probably can't read that in the back, but the RISC-V ISA looks kind of like a standard RISC instruction set. You've got loads, stores, shifts, arithmetic operations, logical operations, compares, branches, that sort of thing. So it's pretty familiar if you've done any hacking on any RISC ISA in the past. At the bottom, you can see some of the instruction formats. They're designed to be efficient for hardware implementers. The rest of the sheet actually shows the optional compressed extension. So they have some extension for better code density. And then the back of the sheet has some of the other standard extensions, your multiply, atomics, and floating point, all that stuff. And there's enough room to actually include the RISC-V calling convention. So it's a pretty kind of lean ISA. So you can look at the specs for the details. I'm sure you couldn't read that, but the specs are online. So you can check out the user-level ISA specification, version 2.1, to find out the details of what the instructions look like, what do branches look like, that sort of thing, what do loads and stores look like, what kind of arithmetic operations are available. The privileged ISA specification is in version 1.9.1. So the privileged ISA is actually, this is the kind of interface that the OS and firmware uses. This is actually in development, so version 1.10 will be released soon. If you want to look at the specification sources, if you want to look at the actual LaTeX sources for these specifications, you can actually find them on GitHub as well, because it's an open standard. So now that we talked about the ISA as a whole, I'm going to talk about the RISC-V hardware landscape, some of the open source SoCs and cores that are available. So there's a lot of RISC-V cores and SoCs, and they're designed for many different use cases. So some of the main use cases are education, research, and commercial products, and we'll see some examples here. And so you have cores that are really designed for small, low-cost microcontrollers, and then you also have high-performance, multi-core chips as well. And you'll see more of this over time. RISC-V is still fairly new, and you see a lot of cores popping up and a lot more people developing RISC-V now than you did even a year ago. And these cores are written in a variety of hardware description languages, or HDLs. So the ones you've probably heard of are VHDL and Verilog, and so there are RISC-V cores, many of them that are written in VHDL and Verilog. Some other languages that you may not have heard of are Chisel and BlueSpec System Verilog. And so these are newer HDLs that are a bit higher level and in some ways a bit more productive. So some of the Berkeley cores are actually written in the Chisel hardware description language. So I'll quickly talk about UC Berkeley and SiFive and the relationship there, just because a lot of the cores that I'll be talking about originate at Berkeley and SiFive. So the Berkeley architecture group, UCB's bar group, created RISC-V. So this is Chris Stasanovich and David Patterson's group. As they were developing RISC-V, they also developed a number of open source cores and SoCs for research and teaching. And eventually, the RISC-V, so the graduate students, Andrew Waterman, Yunsuk Lee, graduated, and they wanted something to do, so they decided, hey, this RISC-V thing's kind of cool, and so they decided to found a company called SiFive with Chris Stasanovich, and they basically designed custom RISC-V chips for customers, and they're building on their open source cores to do that. So it's kind of cool that they're actually they're a company that's doing open source stuff, and they continue to contribute back to the cores that they built at Berkeley. So some of the Berkeley hardware that's out there. So for the system on chip, there's the Rocket chip, and it's a parameterized RISC-V SoC generator. Because it's parameterized, you can tweak the different knobs. There's a number of knobs that you can tweak. So you can tweak the cache hierarchy, the number of cores, the TLB size, whether there's a floating point unit, whether there isn't. And it makes it really easy. You basically go into a config file, and you can tweak the core to your needs. In addition to the system on chip, there are a number of cores you can choose from. So the Rocket core is kind of the standard core that many people use. It's a 5-stage pipeline, single issue. There's also Boom, which is an out-of-order core. It's a research project by Chris Celio at Berkeley. And it's actually pretty cool that you can study the source code of an out-of-order core. There aren't that many out there for people to study. Berkeley also has a set of educational cores called SODER. They're 1 stage all the way to 5 stage. And they're designed for simplicity so people can understand them in university courses. And you can find all the code on GitHub, which is pretty cool. So quick note about the Rocket chip SoC generator. So as I mentioned, it's a parameterized SoC generator. And it's written in this Chisel HDL. And so Chisel is this new hardware description language from Berkeley that's an embedded Scala DSL. And so Berkeley uses it, and SiFive uses it for all of their cores. And so by using the Rocket generator in Chisel, you're able to target a few different backends. So you can target a C++ software simulator, which is basically an executable that simulates your RISC-V core. You can target an FPGA by targeting the FPGA tools, for instance, your Xilinx tools. Or you can target some of the ASIC tools like Synopsys or Cadence. And so the nice thing about the Rocket chip SoC generator is because it's parameterized, it's designed for customization, you can use this as the basis for your SoC. It's all open source, and you can kind of tailor it to your application. So as I mentioned, you can either target FPGAs or actual real hardware, and so SiFive has been doing this, and they've been building on the Rocket core and the Rocket chip SoC generator. So they have 2 platforms now, the Freedom Everywhere, which is their low-cost 32-bit microcontroller product, and they have the Freedom Unleashed, which is the high-performance 64-bit multi-core SoC. So this is kind of the Freedom Everywhere will run your kind of like real-time embedded operating systems, and the Freedom Unleashed will run Linux, BSD, that sort of thing. And you can find their code on GitHub as well. And so here's the cool hardware. So SiFive has these FPGA development kits. And so the RD board, which is about $100 on the left, is about $100 US, and you can use that to emulate the Freedom Everywhere, so the microcontroller class. And so they have a little display hooked up. On the right, it's Xilinx VC707, and it's emulating the Freedom Unleashed. So this is the general purpose core that runs Linux. And so the cool thing that you can probably see is that they're running Doom, and they actually did this demo at the last RISC-V workshop. And so it's kind of cool that you can run Doom on a RISC-V hardware. It was kind of a pretty cool demo. So RISC-V's kind of making progress. So FPGAs are cool. I really like FPGAs, but even more exciting is that there's actually RISC-V silicon now. So the Hi-Fi 1 board is the first generally available open source RISC-V silicon. there were people who had RISC-V silicon, but basically they fabricated themselves. So you either had to basically fabricate your own RISC-V chip or borrow one from a friend. But now you can just go on Crowd Supply and buy one for yourself. So the Hi-Fi one has the Freedom Everywhere 310 SoC. So this is the microcontroller core. It's Arduino compatible, and it supports the Arduino IDE. And it's about $59 US from Crowd Supply. And SiFive was kind enough to donate 3 boards. So I will be giving 3 boards away at the end of the talk for people to play with and hopefully port some more open source software and just do that kind of thing. So the chip in the Freedom Everywhere, the Freedom Everywhere 310, the chip in the Hi-Fi 1 is open source. So all the RTL source code, FPGA scripts, board support packages are all on GitHub, and you can find the documentation, board schematics there as well. So that's actually pretty cool. Another interesting project, another interesting SoC, RISC-V SoC, is the LowRISC project. And some of you may have seen the talk 2 years ago here at FOSDEM that Alex Bradbury gave about LowRISC. So LowRISC is based at the University of Cambridge, and they're aiming to build a really low-cost development board. Their tagline is Raspberry Pi for grown-ups. And it's so it was actually founded by one of the founders of Raspberry Pi. So they basically want to create a completely open version of the Raspberry Pi. So that's actually, I think, pretty cool. And it also builds on the rocket ship SoC generator from Berkeley and SiFive. And they're doing some interesting research things with tagged architectures for security and minion cores for I/O offload. And they have a couple tech notes about this. And I think they're doing some pretty cool stuff. And yeah, you should definitely check out Alex Bradbury's FOSDEM 2015 talk and just follow their progress in general because they're doing interesting things. And their code is also available on GitHub. So the Shakti cores from IIT Madras are another set of RISC-V SoCs. So RISC-V apparently is the standard ISA for India, which is kind of cool. And so as a result, IIT is building 6 open source cores. And they're like literally going from microcontrollers to supercomputers. And so there's a lot of people building a lot of RISC-V hardware there, which is pretty cool. And they're using BlueSpec System Verilog as their HDL of choice. And you can find their code on Bitbucket, not GitHub. And so some other RISC-V SoCs and cores that are available. There's Pulpino from the ETH Zurich. There's Pico RB32 from Cliff Wolf, and this is meant to be a really size-optimized RISC-V implementation, 32-bit RISC-V implementation. And there are a lot of other commercial and open-source RISC-V cores that are out there, like too many to name. It seems like there's a new RISC-V core popping up every day. I mean, there's a lot of people who are just kind of trying to build their own RISC-V core, which I think is pretty cool, because RISC-V is an open standard. If you're a hacker, you can just go and build your own core, which is, I think, pretty cool. So if you want to customize RISC-V, I mean, the nice thing about RISC-V is it's designed for customization. The easiest way to do it is to modify the tunable parameters of an existing core. So basically, you'll just grab the rocket ship and then play with some of the parameters, disable the floating point unit, mess with the cache hierarchy, etc. You can implement your own RISC-V accelerator. You can implement your own RISC-V instruction set extension. Chapter 9 of the user specification has some information on this. And if you think it's useful enough if you think it might be useful to other people, you can submit it for standardization. And if you have a lot of time on your hands, you can implement your own RISC-V core. So yeah, there's been a lot of interesting stuff happening on the hardware landscape. So on the software landscape, in the last 6 to 12 months, there's been a lot of stuff happening as well. So just to kind of give you an idea of what development platforms are available. So if you don't actually have FPGAs and you don't have RISC-V hardware, you can use a RISC-V emulator. So Spike is kind of the standard RISC-V simulator. So it's also called RISC-V ISA Sim. It's kind of the golden model. So every time a specification update is released, the changes go into Spike. In addition to Spike, there's also QEMU, which many of you are familiar with. So the QEMU has RISC-V support, but it's not upstream yet. But it supports, we have support for full system and user emulation. So this is actually pretty cool. So there's another simulator called RISC-V EMU, built by Fabrice Boulard. And you can boot RISC-V Linux in your browser, which is, I think, pretty cool. you should all go do that now and see if you can crash. No, don't do that now, but it's pretty cool. So it was kind of funny. So for Brice Billard is one of these guys who's just like, I don't know, just super productive. So I get an email from him, and he's just like, oh yeah, so I built this small project. It's this RISC-V emulator. It boots Linux in the browser. It has 128-bit support and some other stuff. And even Spike doesn't have 128-bit support. So he like, I don't know, I didn't even know he's aware of RISC-V, so it was pretty cool when he was just like, yeah, I got this little project, does all these things. He's an impressive guy. So yeah, RISC-V EMU is worth checking out. And then we also have an in-progress port of Gem5, which is a full system simulator that's used by computer architecture researchers. And hopefully we can get that kind of upstreamed and kind of farther along. So a quick note on Spike and QEMU. So Spike is great for prototyping hardware features. I use it a fair amount. I mean, the nice thing about it is it has a really small and simple code base, and it makes it really easy to add instructions and customize the ISA and everything. But if you're doing software work, I think QEMU is probably a better option. The emulation's faster. It's got a number of handy debugging features. It's got better device support. There are a few rough edges in QEMU RISC-V now, especially with respect to device support, but we hope to iron them out fairly soon. So yeah, but both are good emulators. With respect to the RISC-V toolchain, there's been a lot of progress. So I'm excited to report that RISC-V support will be in binutils 2.28, and the GCC steering committee has accepted the RISC-V port for inclusion. So the port will likely make it into GCC 7.1. So this is due to a lot of hard work by Andrew Waterman and Palmer Daubelt, and thanks to all the GCC maintainers and reviewers for reviewing patches and making this happen. And so I think now that we have the toolchain stuff, I think Linux distros and more of the kind of software enablement stuff will sort of just fall out. The lack of an upstream toolchain, I think, really was slowing down some of the software efforts. So now that we have upstream toolchains, I think the software enablement stuff will go a lot faster. In addition, there's an LVM port in progress. Some of the patches are upstream. Alex Bradbury from the LowRISC project is working on this. There are a number of, he's working on code gen patches. They should go out in the next week or two. His goal is to basically make this the cleanest back end, and he wants the RISC-V port to be the kind of exemplar for all the other architectures that come after it. So he's building a really clean port. And so as a result, it's taking a little bit longer, but I think it's going to be exciting when it's done. There's a lot of people who want to have LVM RISC-V. So we have a lot of RISC-V OS and firmware ports in progress. They're all in various stages. Some are more mature, some are fairly early. So in terms of firmware, the kind of standard firmware right now is there's this Berkeley bootloader, which is kind of an initial firmware, but people are working on core boot and UEFI support, so that's coming online. For Linux, there are ports in progress for Fedora, Debian, Gentoo, and Yocto Poki. So Fedora has about like 2,000 packages building. It's a little out of date. Debian has a little over 1,000 packages. Manuel's in the audience somewhere. You can talk to him about Debian. Yeah, so if you want to talk more about Debian RISC-V, you should talk to him, because it'd be great to get more people working on that. There's a Gentoo port. It's a little out of date, but Palmer will update it as soon as this stuff goes upstream. The Poki distribution, which is an embedded distribution, has been updated recently, and it's actually a reasonable platform if you want to do RISC-V hacking. It's not upstream yet. We'll have to start pushing that stuff upstream as well. If you're a BSD person, FreeBSD actually has pretty good support for RISC-V. There's a couple things that need to be added, but FreeBSD actually has upstream RISC-V support, which is pretty cool. NetBSD has a port in progress. And there are a number of other operating systems that have RISC-V ports in progress, and these tend to be more embedded operating systems. So SEL4, Gnode, Helenos, Zephyr, FreeRTOS, RTEMS, Minute. So the software stack is, it's getting there kind of steadily. And the most exciting thing is that we have a couple operating systems that have upstream RISC-V support. FreeBSD and FreeBSD 11.0, and the Zephyr kernel from the Linux Foundation also has upstream RISC-V support. So that's actually pretty cool. The software stack is starting to come together. There are a number of RISC-V language efforts in progress. For Java, there are people working on OpenJDK and JIX-RVM. There's a Go port. There's a talk about Go at the last RISC-V workshop, so there's a few Google people who are working on Go RISC-V, they're making a lot of progress in a short amount of time. There's people working on OCaml and Haskell support for RISC-V. CompCert is a formally verified toolchain. It's also got RISC-V support. There are people from Rust who are interested in getting RISC-V. It hasn't started yet because they're kind of waiting on the LVM port. But I think once LVM comes in, we'll see a lot more language efforts kind of getting farther along. So there's a lot of action on the RISC-V software front. So what's next? So we're preparing the Linux kernel, and we will be preparing the Linux kernel, glibc, and QEMU patches for upstreaming. So one of the things that's been kind of holding back some of the distros is the lack of upstream Linux kernel support in glibc. So it looks like the Linux kernel support, the patches look reasonable. Some of the maintainers have looked at them, and there's a few issues that need to be fixed, but once they get fixed, hopefully those patches can go in. And then there's some work on glibc as well. There's also some more work on standards. We need to flesh out our ABI specification. We also need to work more on the privilege specification because it's not a frozen spec yet. It hasn't been ratified. So there's some more work to be done there, and this will be done sort of in parallel with the upstreaming of the Linux kernel and glibc stuff. So as I was saying, once the Linux kernel and glibc get upstreamed, we're going to continue. It'll make it a lot easier to do Linux distros. So we'll continue to kind of improve and update our Linux distro support and upstream those changes. And if there are any distro people in the audience, we'd love your help with getting RISC-V on your distro. And in general, we want to port more software packages to RISC-V. So if you're a maintainer of any software packages, we'd love to work with you to add RISC-V support. And yeah, so in general, we need your help to push RISC-V forward. We hope you'll kind of join the RISC-V community and kind of help with some of these software tasks as well as some of the hardware stuff and documentation as well. So if you do want to get involved, there's some resources that you can check out. So all the code's on GitHub, so that's the GitHub organization. We have mailing lists for hardware development, software development, and development of the ISA. The RISC-V workshop proceedings are online, so both the slides and the talks. And this is a good way to kind of get up to speed with what's been going on in the RISC-V community. There's a Stack Overflow, so if you have questions about RISC-V, you can ask them here. Once you learn more about RISC-V, you can answer the questions. That would be great too. There are a couple articles in Microprocessor Report that sort of describe the RISC-V ISA in general. If you're new to RISC-V, these are worth reading. So the first one kind of talks about the rationale for having an open ISA, and then the second one talks a little bit more about RISC-V particulars. There was an IEEE micro article written by the Berkeley folks about their agile approach to building hardware and RISC-V microprocessors. And that's kind of interesting because a lot of what they're doing is they're using open source and the Chisel HDL, a higher level HDL, to build hardware more quickly. So there are a number of upcoming RISC-V events. If you're able to, it'd be great if you could come to some of the events. It's a great way to kind of meet the community and get involved. So May 9th and 10th, there's the 6th RISC-V workshop. It'll be in Shanghai, China. This is the first time the RISC-V workshop has been outside of the US, so that's pretty exciting. It's hosted by NVIDIA and I forget the name of the university, Shanghai, yeah, let me remember. And then March 14th to 16th, there's Embedded World, so a number of RISC-V Foundation companies will be exhibiting there. April 2nd to 3rd, IIT Madras is having a RISC-V conference. And so they've been doing a lot of work with RISC-V, so you'll hear more about their Shakti cores, and then you'll also hear about RISC-V projects from all around the world. So that should be a cool event. September 8th through 10th, there's ORConf in Hebden Bridge, UK. So ORConf is actually an open RISC conference, but they've kind of opened it up to RISC-V people, so there'll be a fair number of RISC-V talks there as well. So in summary, RISC-V is an open instruction set specification. You can grab it, you can do you can build proprietary cores, you can build open source cores. You don't have to worry about getting sued, which is good. And because it's an open instruction set specification, there's a lot of open source cores that are available. So there's several options. I talked about the rocket ship, LowRISC. There are a number of other options that are available as well. I just highlighted a few of them. The RISC-V software stack is steadily coming together. Things are getting upstream, distros are happening, and we'd love your help there. And in general, we're looking for contributors all across the hardware software stack. So the takeaway is that you should hack on RISC-V, and I hope to see you at one of the many 2017 RISC-V events. Thank you. Sorry, could you speak? Yeah, so this is one of these things that's sort of difficult. So I think the question was about what peripherals are available in the SoC.
And especially what bus you use to communicate with those peripherals.
And the bus. So AXI. Right, so this is a question about specific implementations. So for the rocket ship implementation, the bus they use is AXI. And they have, I don't know, they have SPI devices, PWM. They have, I actually can't enumerate all, they have some GPIOs. So this is one of these things where there are some devices, but there's going to be more work that needs to be done. And so I think the Free Chips Foundation, the FOSDEM Foundation, LibreCores, I think together we'll have to work together. So there are some peripherals there in the SoC. I don't remember all of them offhand, but there definitely will need to be work there. There are no GPUs, for instance. That's difficult. But for a lot of the embedded peripherals, some of that stuff is there. I think we have USB now, maybe. I don't know. So that's an implementation question, and so it depends on the implementation. So the ISA, I mean, it really depends on the implementation. So the Hi-Fi board can be clocked at 320 megahertz. They're using a TSMC 180 nanometer. The Freedom Unleashed platform, they've quoted, they're going to use, I think, TSMC 28 nanometer. You can clock that at 1.6 gigahertz. Above 1.6 gigahertz and above is what they've quoted as. So it sort of depends on the implementation. Yeah. Actually, do you want a board? All right. Anybody else? Yeah. You. Yeah. Yeah. That's a good question. Yeah, that's a good question. So the question is, so the next RISC-V workshop that's outside, the first one that's outside the US is going to be in China, and sort of, what about Europe, I think was the question. And
The question is just when you foresee that it will come to Europe.
Yeah, so actually we were hoping to come to Europe, just because of the timing. I mean, there were a couple venues that were discussed, like Cambridge and Zurich, and it was mostly a timing thing. So we're definitely going to come to Europe. It was just the dates that we've set up were kind of difficult with university calendars and things like that. There will be some RISC-V meetups that we haven't scheduled yet, but we're hoping to have a couple of RISC-V meetups. There'll be smaller events in Europe. But yeah, we definitely want to have a foundation event soon in Europe. Probably, I think the next one will probably be in the US, but hopefully sometime next year we can get to Europe. But there are a lot of other, we'll definitely be holding smaller RISC-V events. Sorry, what was that? I don't know about this year. So the question was, will some of the RISC-V founders come to ORConf? So, yeah. So they've been to ORConf in the past, like 2 years ago, they gave talks there. I don't know if it'll happen this year, but I'll see if they can make it, or some other RISC-V people. But yeah, I think in general we should get more RISC-V people going to ORConf events and coming to Europe. You get aboard too. Does anybody else want to?
Yes. Here.
Where? Oh, yeah.
The guy with the microphone.
You got a
Thanks.
microphone. All right, yeah.
So now that you've tackled the CPU, and thanks, how about pretty please with sugar on top, start tackling the GPUs?
Yeah.
Please.
Yeah. That's a good question. Yeah, so the GPUs are hard. There are some, I know there are some academic efforts that are building their own GPUs. I think the RISC-V Foundation and some of the other, like FOSDEM Foundation, and there's a new Free Chips project that's been founded, and basically they're kind of taking over some of the, they're playing the foundation role for the rocket ship. So their goal is to build more open source IP blocks. I think the GPU is going to be hard. We need to get a lot more people kind of working on that. So I think it's probably going to require collaboration between all of the open hardware projects. But there are a couple of academic projects that look promising.
Which ones?
I don't remember, honestly.
But what's the search for? Something probably.
Yeah, I don't remember where they're from. Yeah, Open GPU University. I don't know. I'll see. I'll ask some people about it because I remember hearing about a couple that seemed kind of promising. I mean, the other thing you can do is just post to the RISC-V mailing list, hardware dev, and just get a discussion started. It's not a priority for us right now. There's a lot of other things we have to work on, but I think as the open hardware community as a whole, together, we should definitely tackle that. Yeah, GPUs are hard. Open GPUs are hard too. Sure. Yeah, we'll get you afterwards.
Is there beside the instruction set that you've shown here today, do you have any ideas about something like SIMD?
SIMD. Okay, so there's a vector extension that that Krista is working on. So Krista apparently has worked on like vectors, like vector machines, kind of like his whole career. So he and some other old school vector people are really excited about putting like a vector proposal together. So there's been some discussion about it, but it's going to take a while to kind of standardize. If you're interested in that, you could talk to people on the ISA Dev mailing list, or we also have working groups at the RISC-V Foundation meetings. So there are people who are interested. Krista in particular is all about vectors, so something will happen. I can't promise anything in terms of timeline. So, someone here had a question. Yeah.
Okay, small question. Are those SiFive 31 chips available for the public and for your own designs or just on the board?
Oh, sorry. So you want to buy a SiFive chip?
Yeah, just a chip, not the board. Are they available for your own designs or?
I'm sure if you email SiFive, they'll sell you some chips.
Okay. So you don't really know?
Yeah, I mean, so what their business model basically is that they'll do custom design for you. So I'm sure they'd be happy to sell you chips if you have some sort of board that you want to build or something. It's a pretty nice chip.
About the openness, you mentioned a lot of times that it's open and there are no lawyers involved and there's nothing to be afraid, just copy the implementation of the course and edit. What's the license? And are there any patent issues? And is there one license for all implementations?
That's a good question. So the question is about licensing. So the license depends on the implementation. So the Berkeley core is under the BSD license. SiFive's licensing some things under Apache. Other people are using the ISC license. I'm sure there's some copyleft like GPL hardware as well. So it's sort of up to the project to decide what license they want for their specific implementation.
It can be proprietary as well.
Yeah, absolutely. It can be proprietary as well. So if you're a company, and there are several companies doing this, because it's just a standard, you can implement your proprietary RISC-V chip, and that's completely fine. Yeah. All right. Is that everybody?
Hi. What peripherals are available on the RISC-V MCU that we're selling now? Or
Yeah, okay, so...
like SPI, I2C?
Yeah, so it has some SPI, it has some GPIOs, it has some PWMs. I don't remember everything else. The crowd supply page will have all the details. But it's Arduino compatible, so you can put like Arduino shields in there. So there's a couple Adafruit shields that they use in their demos. So I don't remember all of the details, but if you go to the Crowd Supply website, it has all the details and there's a data sheet. Yeah. Sorry, there's a question back there.
Hardware implementations using multi-threading.
So the question was, are there implementations using multi-threading? So there are multi-core implementations. Are you talking about like symmetric multi-thread, like hyper-threading?
Talking about using a single pipeline but having maybe several program counters, several register banks, and you can select which program count to use every cycle. Fine-grained multi-threading.
Yeah, I don't know. They may exist. I'm actually not sure. I don't think the Rocket chip does that. I think the Rocket chip is just multi-core. So it doesn't have like hyper-threading or anything like that, or SMT. There were some questions back there. Okay. Okay, so the question was, what's the risk? Are the specifications frozen, and what's the risk about if you buy hardware that it doesn't match the specification? So the nice thing about, the specific, the Hi-5 1 board only implements the microcontroller spec, so, or it's a microcontroller, so it doesn't implement the privilege specification. So the stuff that it implements is frozen. But the privilege spec is under development. So hardware that is using the privilege spec, there actually isn't any generally available, but that could be a problem there. But we're hoping to standardize the privilege spec this year. So hopefully none of the I think it's unlikely that hardware will be out that doesn't match the spec that's generally available. I mean, you can build your own test chip. Several people have built test chips with the earlier version of the privilege spec.
So two things. As you mentioned GHC, the Haskell compiler, it's actually pretty easy to add basic architecture support to GHCs. You just have to like edit 2 lines of Haskell code or something and like autoconf. I've actually been doing that in the past quite a lot for like Super H, which is like now being redeveloped as an open source architecture. And the second thing in general is, so I'm a Debian developer, and in Debian we have this project called Rebootstrap. I don't know if you've heard of it. It's basically like an automated system which allows you to cross-bootstrap a new architecture. So it's an amazing effort, and you just run a simple script, and in the end you end up with like the minimum set of packages cross-built for the new architecture that you need to be able to bootstrap, and meaning that you can build it on the the Debian build-D infrastructure. And the nice thing is that it's constantly running on a Jenkins job, so we are like basically verifying all the time, like if something is cross-bootstrappable or not, or a package is cross-buildable. And so with this mechanism, we are actually fixing all the bugs and making new architectures built on Debian, and we of course upstream all that stuff. So and OpenRISC is included in that.
Sounds cool. Manuel, I guess you know about it.
Sorry.
Sorry, I was talking to Manuel because he's done the Debian RISC-V port. I was like,
who?
Manuel.
No.
Yeah. So he's our Debian guy.
Can I get a board?
Sorry. I think these 2 guys get one. If I have more, yes. There was a question there, yeah. Yeah. That's a great question. So there's a question about whether there's a certification program to make sure that the standard is followed. So that's actually something the RISC-V Foundation is working on. So it's kind of key that we're building up these compliance tests, and so we need to and that's kind of like going to verify that you are meeting the RISC-V standard. There's also been some work on building a formal specification of the RISC-V ISA, which is a little bit different, but related. So that's in progress, but it's still pretty early.